Professor Adriansens will join us in the next segment. Now in this lecture, we're going to continue by taking a deep look and compare two structures, the Berlin Central Station and the Dutch Maritime Museum. Both are examples of excellent design and represent contemporary vaults of meshed steel and glass. The Berlin Central Station was designed by the engineering firm Schleich Bergermann and Partners in collaboration with the architecture firm Van Gurken Marg and Partners, abbreviated GMP. The Dutch Maritime Museum was designed by Laurent Ney and Partners. Berlin Central Station is located just to the west of where the wall had stood and where the old Lehrter train station once was. From a symbolic point of view, when Berlin became the capital of a reunified Germany, a transportation hub in Berlin was needed to efficiently connect the East and the West. The transportation hub would need to reconnect the tram with the regional, national, and international train systems. A design competition was held, and the winning team was Schleich Bergermann and Partners with GMP architects. The overland tracks run along the east-west axis, and the office and retail building that straddles them runs north and south. As Claire Olson and Sinead McNamara from Syracuse University wrote in their book, Collaborations in Architecture and Engineering, quote, "These formal gestures of the structure mimic a stitch that is knitting the fabric of East and West Berlin back together." The structure that I want to highlight regarding the central station is the glass and steel roof over the east-west tracks. The roof covers 6 tracks and 3 platforms. If you take a close look at this image, you will notice some cables below the steel arches. They serve an important purpose because the arch, due to its form, would be under bending if the cables did not exist. And the most efficient way to engage an arch in carrying loads is under pure compression. A sketch of the steel arch shows the structural details of the roof. You can see the steel cables go below the arch in the center, but they protrude out of the arch at the ends. There's a rationale for this. Before I explain the engineering purpose for these cables, let me discuss how this form for the structure came about. Ideally, under gravity loads only, an arch would be under pure compression and no bending. But this only happens when the form of the arch is correct. In this case of the Berlin Central Station, the roof would need to be quite tall to make it a pure compression form, and the architect argued against this solution. The most efficient form for a vault places the material only where needed and avoids bending. To create a light and efficient arch form, the solution for the train station was to use the steel arch as the compression element and steel cables as the tensile element. Even once the solution was agreed upon by the architects and engineers, there are still design choices that need to be made, some of which are based on material and spatial constraints. For example, what would be the distance between the tension and compression elements? And where do the tension and compression elements cross, creating points of zero bending, referred to as hinges? The answers to these two questions are actually related to one another, as I will illustrate in a moment. To demonstrate the relationship between the form of the arch and the forces of the compression and tension elements, we will use an analysis technique called graphic statics. You will learn the details of how to use this method in the structural studies, but here I present the basic idea, starting with a cable in tension as seen in suspension bridges, for example. On the left is a string or cable that has one load in the center. The shape that it takes is intuitive. To proceed with the analysis, you need to have one constraint, either a magnitude of force or the sloping angles of the cables. In this case, let's assume we know the cable slope. To draw what's called the force polygon on the right, first you draw the vertical load. The length that you draw that vertical load, called the load line, represents the magnitude of vertical load. For example, you can set the scale equal to 1 centimeter equals 5 kilonewtons. Then you draw on the force polygon the 2 parts of the cable with proper slope, meaning you draw parallel lines. These 2 lines will intersect at what's called the pole. The lengths of these lines represent the force in the cable, and the length is automatically scaled to that which you drew the vertical load. So, for example, if your vertical load was 5 kilonewtons and you drew that line to 1 centimeter, and the lines representing the cable is 3 centimeters, then you have 15 kilonewtons of force in the cable. The same procedure can be applied to 2 loads, 3 loads, as many loads as you want. You'll notice that the form approaches a parabola as seen in suspension bridges. How do we apply this concept to arches? Actually, you apply it in the same way. The result is that the diagrams are flipped. A string or cable will automatically deform to follow the path of the force, which is equal to the line defining the deformed shape. However, for an arch, this line defining the path of forces, called the thrust line, does not necessarily have to coincide with the actual arch structure. One can build an arch form in many ways. If the arch center line coincides with the thrust line, there will be no bending moments in the arch. But if the arch center line is built outside of the thrust line, there will be bending moments in the arch. The value of the moment is a function of the perpendicular distance between the thrust line and the arch center line. For example, the moment at point 1 equals the force in the thrust line. We will call that N1, which is equal to the value of the solid yellow line in the force polygon. So you multiply N1 times D1 to get that moment at point 1. And you follow the same procedure for point 2. Let's apply this knowledge of graphic statics to understand the form of the arch in the Berlin train station. I credit some students at Princeton University who did this analysis as part of a class assignment. They used a methodology illustrated by Philippe Bloch's group at the ETH in Zurich. First, you must select where the hinges will be. This is a location where the thrust line crosses the center line of the arch. With a slightly more advanced graphic statics technique than that which I demonstrated earlier, one can then find the thrust line for the arch. The thrust line is then superimposed on the steel arch for the train station. One sees that they do not coincide, so there will be bending moments in the arch. Now don't get confused, the thrust line is not the position of the cable. Next, we'll find the position of the cable. We can assume that the tensile force in the cable, which we will call T, remains constant. The distance between the steel arch and the cable we will call E. Recall that the moment is equal to the thrust line force times the distance between that thrust line and the arch at any point along that arch. We must counteract the moment that the steel arch has due to that distance d with the action of the cable. The equilibrium condition is defined by a sketch that includes the thrust line, the arch, and the cable. From the sketch, we know that the thrust line force times the distance d is equal to the tension in the cable T times E. Therefore, at each point in the arch, the value of E can be determined by E equals N times D divided by T. In the design process, we have a choice as to what value of T to use, and that choice comes by varying the material strength and/or the area of the cable. Since E is inversely proportional to T, the larger the T, the smaller the E. The diagram shows 3 different cable designs, each with a different value of T. You can see that for the largest value of T, we have a small distance between the arch and the cable, where for the smallest value of T, we have a larger distance. We can also vary the shape of the cable by changing the positions of the hinges, as shown in this sketch, where the further out the hinges are, the deeper that distance is in the center. And the closer those hinges get to one another, the more shallow that distance is in the center between the cable and the arch, but the deeper it gets on the outside. The methodology that we applied here can apply to other free-form arched curves. For example, the arch on the bottom is not symmetrical. You can see how different the cable layout is. This is a design for the Waterloo International Railway Station. We have just completed an in-depth examination of a structure with old materials, glass and steel, and we analyzed it with old tools. Even so, the form is relatively new. It's a modern form of a barrel vault. Next, we'll look at another structure of steel and glass, the one that we are standing under now. You will see that even though it uses the same materials of steel and glass, the form and the way that the form was derived is completely different and new.